The second data release of the LOFAR Two-Metre Sky Survey covers 27% of the northern sky, with a total area of approximately 5,700 square degrees. It achieves high angular resolution of 6 arcsec, enabling optical identifications of a large fraction of detected radio sources without further radio follow-up. The process is challenging due to the many extended radio sources found in LOFAR images. The authors employ a combination of methods, including a likelihood ratio crossmatch method, a citizen science project, and new approaches to algorithmic optical identification, along with extensive visual inspection by astronomers. They present spectroscopic or photometric redshifts for a large fraction of the optical identifications. In total, 4,116,934 radio sources lie in the area with good optical data, of which 85% have an optical or infrared identification, and 58% have a good redshift estimate. This dataset is the largest ever optically identified radio catalog, permitting robust statistical studies of star-forming and radial-out active galaxies. The survey aims to survey the entire northern sky at a central frequency of 144 MHz, providing an unrivaled resource for wide-area low-frequency selection of extragalactic samples. Identifying optical counterparts for radio sources is a complex task, particularly in large surveys, due to the limitations of low-resolution surveys. Higher resolution surveys are essential to accurately match radio sources with optical data. The process of optical identification is further complicated by the physical size of radio structures, requiring both association and identification of radio components and their optical counterparts. The Radio Galaxy Zoo project, a citizen science initiative, has contributed significantly to providing associations and optical identifications. The LoTSS surveys, with their capability to detect extended emission on scales up to 1 degree and good resolution, aim to provide the ancillary data necessary for scientific exploitation. The first LoTSS data release, DR1, included an optically identified catalog generated by combining LoTSS data with pan-STARRS and all-WISE data. This catalog provides a valuable resource for researchers, enabling the investigation of radio sources in unprecedented detail. By leveraging the high-resolution capabilities of LoTSS, the catalog facilitates the accurate identification of optical counterparts, overcoming the limitations of previous surveys. The LoTSS survey's high resolution and sensitivity enable the detection of extended emission, allowing for a more comprehensive understanding of radio sources and their optical counterparts. The combination of LoTSS data with pan-STARRS and all-WISE data provides a robust framework for identifying optical counterparts, ensuring a high degree of accuracy and reliability. This refined dataset offers new opportunities for scientific exploration, enabling researchers to investigate the properties and behavior of radio sources with unprecedented precision. The process of deriving optical identifications for LoTSS DR2 targets involves datasets used for the optical counterpart catalog and an approach to likelihood ratio cross-matching. This includes the public Zooniverse project, Radio Galaxy Zoo, LOFAR, which provides outputs through post-processing of Zooniverse and likelihood ratio identifications and associations. The summary also covers source angular sizes, methods for estimating photometric redshifts, galaxy masses, and other physical quantities. The final catalog is described, along with properties of the sources in the resulting catalog. The cross-matching of radio sources to their optical and infrared counterparts is achieved using a likelihood ratio method, combining data from the legacy survey and WISE to create a joint catalog. This process is region-specific to account for differences in optical survey properties. The decision tree used for selecting radio sources includes the exclusion of faint sources below 4 mJy and the incorporation of machine learning classifications to reduce visual sorting requirements. Machine learning classifications predict outcomes for DR2 sources, selecting most sources for direct processing in RGZ, L, and reserving visual sorting for a smaller, more complex subset. The optical IDs for LoTSS DR2 have been processed, with a total of sources classified. The decision tree used in the PYBDSF catalog processing includes optical and IR identification, RGZ, L, processing, and artifact rejection. Faint sources have been excluded, and the confidence in the ML approach for inspecting unusual sources is highlighted. A comprehensive analysis of various clustering methods is presented, applying LR, NNLR, and RGZ, L, to a dataset of 1,149,814 objects. The LRID method successfully identifies 28% of the objects, while the no ID category accounts for 3.6% of the dataset. The flux ratio criterion is employed to separate objects, with 0.15% falling into the no ID category. The M-source workflow is utilized to identify faint objects, resulting in 1.6% of the dataset being classified as such. The RGZ-L method is applied with different blending and zooming techniques, yielding varying results. The artifact category accounts for a small percentage of the dataset, ranging from 0.0059% to 0.029%. The uncat host category, representing unidentified hosts, makes up a significant portion of the dataset, ranging from 0.37% to 1.37%. Visual sorting is employed to categorize objects, with the MLLGZ method used to identify faint objects. The results of the RGZ-L method with different blending and zooming techniques are presented, highlighting the effectiveness of each approach. The analysis provides a detailed understanding of the strengths and limitations of each clustering method, informing future work in this area. The results are crucial in understanding the effectiveness of each approach, with the RGZ-L method yielding varying results depending on the blending and zooming techniques employed. In the decision tree, the primary branch defines parameters for large optical galaxies, specifying a minimum size of 60 arcseconds, a major axis greater than 15 arcseconds, and a total flux density above 8 mJy. Additionally, the tree considers isolation from nearby PYBDSF neighbors and the presence of a single Gaussian component within an island. The tree's outcomes dictate post-processing steps, which are further refined through machine learning classification and visual inspection. To facilitate visual inspection, citizen scientists were engaged through the Zooniverse platform, where they reviewed radio and optical images, including a color map version of the radio image. The interface enabled flipping between views and featured a multicolor optical image to enhance accessibility. The field of view was algorithmically selected to maximize the probability of capturing all components of a large source, involving iterative addition of nearby resolved neighbor objects until convergence. The final analysis integrated citizen science classifications with those from the collaboration, ensuring a comprehensive and accurate assessment. This multi-step approach enabled the precise identification of large optical galaxies, leveraging the strengths of both machine learning algorithms and human visual inspection. The decision tree outcomes are discussed, focusing on various IDs such as those indicating no identification, large optical galaxies, and sources sent to the RGZ-L for further processing. The process of classifying radio sources involves the use of tutorials and videos to educate volunteers. Additionally, refinement is added to retire sources after a certain number of unclassified views to avoid wasting user time. The results from RGZ-L include the number of sources processed and the quality factors for associations and identifications. The Zooniverse platform has facilitated the classification of radio sources, yielding 957,374 classifications from 13,711 users. Analysis of user participation reveals a power law distribution, where a small fraction of volunteers, approximately 125, contributed half of the total classifications, while a larger group made only 1 or 2 classifications. This suggests that a dedicated group of volunteers has developed expertise in classification. The raw optical identification rate from the Zooniverse project is relatively low, with only 27% of sources yielding a consensus optical ID. However, a visual inspection of a randomly selected subsample of RGZ-L optical IDs by 2 independent astronomers reveals an error rate of approximately 3%. This indicates that the optical ID process is conservative and accurate, underscoring the reliability of the classification results. The Zooniverse volunteer population's classification statistics and consensus on optical IDs are analyzed, revealing a power law distribution of classification numbers with a slope of approximately 1. This indicates that a small number of volunteers contribute a large proportion of classifications. The distribution of optical ID consensus scores follows a median of 0.6, suggesting that at least 3/5 of volunteers agree on the optical ID for a given source. Notably, a few volunteers exhibit high consensus scores, potentially indicating that they only classified obvious sources. To address this, the consensus scores are used to reweight the optical ID votes, resulting in an improvement of the optical ID fraction from 25% to 31%. The supplementary catalog, containing hashtags assigned by volunteers, enables easy searching and querying of the data. However, the paper notes the limitations of the morphological tags applied, advising against their use for complete samples. The generation of the RGZ-L catalog is described, involving the merging of decision tree results with radio and optical catalogs. This process enables the creation of a comprehensive catalog, leveraging the strengths of multiple datasets. The LoTSS DR2 dataset has been utilized to generate an optical identification catalog. Figure 6 exhibits examples of RGZ-L subjects, comprising optical and radio contour images, with optical IDs selected by Zooniverse platform volunteers marked as green crosses. The top row demonstrates cases where a consensus was achieved, and the correct optical ID was selected, whereas the bottom row illustrates instances where no consensus was found, and no optical ID was returned from RGZ-L. The catalog generation process consists of two primary components: a source catalog containing essential information and a component catalog that enables the final state of each PYBDSF source to be looked up. Objects flagged as artifacts by a majority of Zooniverse volunteers or during pre-filtering are removed from the catalog. Derived table entries for quantities such as the total flux density of a composite source from RGZ and the maximum size of the convex hull enclosing all components, composite_size, are also generated. A small minority of sources required further visual inspection to ensure catalog accuracy for extended, complex radio sources. This involved 6 workflows carried out by astronomers on the LoTSS team, involving expert classifiers editing either or both the association or identification of the cataloged source. These workflows, executed in a specific order, included: first deblend, 2 zoomed in, TZI, and others. The first deblend workflow involved breaking down PYBDSF components of a single composite source into their component Gaussians, allowing for a finer-grained allocation of radio sources to optical counterparts. The 2 zoomed-in workflow was used for sources where RGZ-L volunteers flagged sources as 2 zoomed-in, indicating extended structure on larger scales than visible in the presented image. The current workflow involves several stages to refine the catalog, including deduplication, to merge duplicate objects; postfilter, for visual inspection of large sources; blend prefilter, to check blend status; and second deblend, for detailed editing of complex sources. The post-filter step flagged around 30% of sources as problematic, mostly due to being too zoomed in. The blend prefilter identified a significant number of blends, with only 13% proceeding to the second deblend workflow. The second deblend allowed for detailed editing of complex sources, including the inclusion of previously unassociated components. Additionally, a version of the Ridgeline optical ID code was used on large sources without an optical ID assigned from visual inspection. The recorded radio source provenance and optical ID sources are detailed in tables 3 and 4, respectively. The final catalog of radio sources details their provenances, including IDs, redshifts, and sizes. Source identification methods are highlighted, with optical IDs playing a significant role. Statistics of these IDs are also discussed. The estimation of radio source angular sizes is emphasized, involving floodfill sizes and manual measurements. The process of determining the largest angular size, LAS, for sources includes manual measurements, composite sizes, and floodfill sizes. The distribution of LAS origins is presented in Table 4. The ANA proofs and manuscript details are built upon the DR2 catalog, which comprises a total flux and fractional optical IDs. A breakdown of these IDs by different methods of optical identification reveals that 73% are secured through spectroscopic redshifts, 14% through photometric redshifts, and 13% through other methods. Notably, sources with genuine low surface brightness extended structure are identified, along with those with fitted Gaussian size estimates, with a resolution criterion of 1.5 times the full width at half maximum. This distinction is crucial in understanding the morphology of these sources. The discussion then turns to redshifts and physical source properties, where photometric redshift estimates are obtained using the LOFAR code. This methodology involves fitting observed spectral energy distributions to a library of templates, yielding accurate estimates with a median absolute deviation of 0.06. The performance of these estimates is evaluated, demonstrating reliability and precision across different redshifts and optical magnitudes. For instance, the estimates are shown to be accurate to within 10% for sources with optical magnitudes brighter than 22.5. Furthermore, spectroscopic redshifts from the Sloan Digital Sky Survey's Data Release 16 are incorporated for matched sources, providing a robust validation of the photometric redshift estimates. This synergy enables a comprehensive understanding of the properties of these sources. By incorporating spectroscopic redshifts from the DAISY survey and HETDEX data release into the LoTSS DR2, the authors increased the available spectroscopic redshifts by approximately 1%. Redshifts exceeding 5 were excluded due to their unreliability. The best redshift estimate was determined based on the availability of spectroscopic and photometric redshifts. Physical properties, such as projected size and radioluminosity, were estimated using the best redshift. A Python-based SED fitting code was employed to calculate stellar mass estimates and rest frame magnitudes for the LoTSS sample. Notably, this approach accounts for photos' uncertainty in the stellar mass estimates. The authors validated the precision of their stellar mass estimates by comparing them to existing values in the literature. This integration of spectroscopic redshifts and SED fitting enables a more accurate characterization of the LoTSS DR2 sample. The authors present a statistical analysis of photometric and spectroscopic redshifts for LoTSS DR2 sources, showcasing the quality of their photometric redshift estimates. Figure 9 illustrates the photometric redshift posterior distributions as a function of SDSS spectroscopic redshift, demonstrating the reliability and accuracy of photometric redshifts. The right panel of Figure 9 displays the distribution of available redshifts for all optically identified objects as a function of Y's band 1 magnitude. The authors compare their stellar mass estimates with those from the GSWLC and Duncan, 2022, catalogs, finding that GSWLC mass estimates are consistently higher by approximately 0.1 dex, with significant scatter. They also compare their estimates with those from the LoTSS deep fields, applying a correction based on the measured Z-band flux to account for differences in photometry measurements. The resulting mass offsets are within 0.1 dex, showing a noticeable dependence on stellar mass and redshift. The authors conclude that their stellar mass estimates are reliable, with no significant systematic offsets from limited photometric information. The observed 0.1 dex offsets are consistent with differences in star formation history assumptions. However, this is only the case for sources with no significant radiative AGN contribution to the observed optical flux. The paper discusses the optical IDs for LoTSS DR2, focusing on the distribution of estimated stellar mass differences compared to GSWLC and LoTSS deep fields DR1 for sources in common. It highlights the need for caution when using stellar mass estimates, especially for sources with significant radiative AGN contributions. The authors provide an additional catalog column, flag_mass, to indicate which stellar mass estimates are safe to use. They also describe the main product as a science-ready source catalog containing all objects thought to be physical sources, along with their radio properties, optical ID information, and associated optical properties. The catalog includes a component catalog, which is an annotated version of the DR2 radio source catalog, with differences such as new component names and the inclusion of deblended components. Additionally, the paper discusses comparisons with the 3CRR catalog, showing a correct optical ID fraction of 57 out of 62, and a good match in flux density for 79% of the sources. The table on page 18 of the research paper presents matches between 3 CRR objects and sources in the final LoTSS catalog. It includes details on the name, ILT name, 3CLAS, LoTSS-LAS, and their matches. The table highlights objects with no optical ID, those with photometric redshifts, and those with spectroscopic redshifts. It also notes the discrepancies in flux density and largest angular size between LoTSS and 3CRR. The LoTSS catalog has a lower resolution compared to the VLA maps used for 3CRR, which might contribute to these discrepancies. The redshift accuracy in LoTSS is only 10% for a few cases, mostly spectroscopic from SDSS, and there are instances where the redshift is not accurate or missing altogether. The LoTSS DR2 catalog optical identification process is presented, with a focus on comparisons with the 3CRR catalog and LoTSS DR1. This work underscores the value of targeted spectroscopic surveys in improving photometric redshifts, particularly for quasars and galaxies with strong emission lines. Notably, the analysis reveals a higher optical ID fraction in DR2 compared to DR1, with a better match for bright and compact sources. Cross-checking IDs against those from O'Sullivan et al. 2023, and Wang et al. 2023, demonstrates good agreement, especially for bright sources. The teapot plot in Fig. 12 illustrates the relation between optical or IR apparent magnitude and 144 MHz flux density, showcasing two distinct branches for star-forming galaxies and AGN populations. This research highlights the importance of a hybrid process combining likelihood ratio matching, heuristics, and visual inspection for creating a reliable optical ID catalog. The hybrid approach leverages the strengths of each method to mitigate the limitations of individual techniques. By combining these methods, the study achieves a more accurate and comprehensive optical ID catalog. The findings of this research have significant implications for the improvement of photometric redshifts, particularly for galaxies and quasars with strong emission lines. Analysis of radio sources, particularly quasars and radioloud active galactic nuclei, reveals crucial connections with optical and infrared properties. The LoTSS DR1 dataset plays a vital role in understanding these relationships. Figure 11 illustrates the fraction of LoTSS DR1 objects with optical IDs matching those in DR2, categorized by their DR2 origin. This plot shows quasars predominantly occupying the right-hand side, while RLAGN exhibit a narrow optical magnitude range due to their prevalence in massive galaxies. WISE color plots, presented in Figure 13, demonstrate the widespread presence of radiosource counterparts across the plot. Normal galaxies and star-forming galaxies occupy distinct regions, highlighting the diversity of radio sources. Furthermore, Figure 14 examines the relationship between mass and radioluminosity, revealing a tight correlation between these physical quantities. Quasars contribute to a horizontal scatter, indicating a distinct behavior. These findings have significant implications for understanding the properties of radio sources and their environments. The LoTSS DR1 dataset provides a unique opportunity to study the connections between radio, optical, and infrared properties, shedding light on the complex relationships between these phenomena. The relationship between radio and optical properties of objects in the catalog is examined through a series of plots. A logarithmic density plot of WISE detected DR2 sources reveals a correlation between total LOFAR flux density and WISE band 2AB magnitude. Focusing on sources with reliable WISE magnitudes and redshifts less than 0.5, a second plot shows a strong correlation between total 144 MHz radioluminosity and WISE band 2 absolute AB magnitude. A color plot of catalogued objects in the WISE space illustrates the distribution of objects with reliable WISE photometry in the radio catalog. This is further divided into two plots, one for all objects and another for a subset with well-defined redshifts less than 4. The discussion highlights the reliability of redshifts from the SDSS quasar catalog for the majority of powerful sources, with a notable absence of very powerful sources at redshifts greater than 4, suggesting environmental or radiative loss constraints. The largest sources are also examined, including one with a nominal size of 6.9 mpc, although its size relies on photometric redshift and angular size estimates. This finding has significant implications for our understanding of the evolution and properties of these sources. The relationship between stellar mass and 144 MHz radioluminosity is illustrated in Figure 14, a logarithmic density plot of radioluminosity as a function of mass for 1,737,778 radio sources with reliable mass estimates and usable W1 and W2 magnitudes. The plot displays the median W1 W2 colors for each cell, overlaid with kernel density estimation, KDE, estimated logarithmic density contours. Notably, the catalog includes 13 candidate sources with projected sizes greater than 4 mpc, all of which are convincing FRII radio galaxies upon inspection, with 4 having spectroscopic redshifts. However, the optical IDs for these large angular size sources should be treated with caution due to the possibility of multiple candidate hosts for each source. There are 8,541 sources with estimated physical sizes greater than 700 kpc, the standard threshold for a giant radio source in modern cosmology. However, careful size measurements are necessary to confirm whether they meet this threshold value. The catalog has several caveats that users should be aware of, including incompleteness primarily arising from the limited availability of optical and IR data. This limitation affects the completeness of the catalog, particularly for low-mass and high-red shift objects. Users are advised to conduct their own tests to quantify and account for the effects of incompleteness for their specific science use case. Additionally, the catalog only lists objects detected in the original DR2 radio catalog, which may introduce detection incompleteness, Eddington bias, and the possibility of sources not being fully deconvolved at the faint end. To mitigate these issues, users can apply a higher flux density cut to the catalog, such as the 1.1 mJy flux density reported to be the 95% completeness limit. The largest optically identified radio survey to date, covering 4.1 million radio sources in the LoTSS DR2 area, has been achieved through the extensive use of likelihood ratio cross-matching, visual inspections by citizen scientists and astronomers, and the internal Zooniverse project. This endeavor required an estimated 6 person-years of human time cost. The resulting science-ready catalog includes high-quality photometric redshifts, spectroscopic redshifts, and derived quantities such as radioluminosity and physical size estimates. Additionally, galaxy mass estimates are provided as a byproduct of the photometric redshift process. A comparison with the bright, extended sources in the 3CRR catalog demonstrates the good quality of the optical identifications and redshift estimates for this class of object. Follow-up observations with WEAVELOFAR will obtain spectroscopic redshifts for most of the bright sources in the sample, which may include many high redshift radio galaxies. The authors emphasize the need to incorporate more advanced matching techniques, such as those using machine learning algorithms, to tackle the increasing complexity of future surveys like SKA and LSST. They also stress the importance of learning from the results of this work and developing more efficient methods for generating optical IDs for the remainder of the full LoTSS Northern Sky Survey. The publicly released catalog is expected to provide a valuable resource for a wide range of scientific projects based on the radio properties of active and star-forming galaxies. Future releases of the catalog will incorporate improved optical IDs, further spectroscopic redshifts, and environmental and radio spectral information. The authors also explore the potential of exploiting the higher resolution provided by the Full International LOFAR Telescope, ILT, to improve the optical identification rate. The authors present a list of 25 critical infrastructure entities, comprising 15 power grid operators, 5 telecommunication providers, and 5 financial institutions. These entities are selected based on their significant impact on the economy and daily life, making them prime targets for cyberattacks. The authors employ a novel approach, combining graph theory and machine learning to model the interdependencies between these entities. This approach enables the identification of critical nodes and edges, which are crucial for maintaining the overall resilience of the infrastructure network. The authors utilize a weighted graph representation, where nodes represent the infrastructure entities and edges symbolize the dependencies between them. The weights assigned to each edge reflect the degree of interdependence, with higher weights indicating stronger connections. A machine learning algorithm is then applied to identify the most critical nodes and edges, which are essential for maintaining the network's connectivity and functionality. The results reveal that a small set of critical nodes and edges play a disproportionate role in maintaining the resilience of the infrastructure network. The authors demonstrate that targeting these critical components can have a devastating impact on the entire system, highlighting the need for proactive measures to protect these vulnerable points. The study's findings have significant implications for policymakers and infrastructure operators, emphasizing the importance of collaborative efforts to enhance the cybersecurity of critical infrastructure entities. The appendix provides a detailed description of the columns in the source catalog and component catalog. The main catalog, outlined in Table A.1, comprises columns for source name, radio right ascension and declination, total flux density, peak flux density, and various error estimates. It also includes columns for the PYBDSF source code, mosaic ID, fitted and deconvolved Gaussian parameters, RMS noise in the island, workflow status flags, prefilter and postfilter status, and likelihood ratio value. Additionally, the table features columns for optical right ascension and declination, as well as composite source properties such as the maximum size of the convex hull surrounding components, transverse size, and position angle. The catalog further incorporates columns from Radio Galaxy Zoo, including association quality, blend probability, and other problem probability. The origin of the radio component assignment, origin of the optical right ascension and declination, and legacy ID, if applicable, are also included. Each column is accompanied by its corresponding Python data type and length in bits and units where applicable, providing a comprehensive understanding of the data stored in each column and enabling efficient analysis and processing of the catalog data. The table provided, a continuation of Table A.1, offers a comprehensive overview of celestial objects' properties. It includes AB magnitudes, morphological models, right ascension, declination, star likelihood, and photometric redshifts. The structure details each object's type, flux fractions, and their uncertainties, as well as flags for source quality, spectroscopic redshifts, and their confidence. Spanning multiple wavelengths including G, R, Z, and WISE bands, the table provides magnitude and error values, making it a crucial component in understanding celestial objects' properties and behaviors within the context of the research. The table on page 27 of the research paper continues to describe the optical IDs for LoTSS DR2, detailing various properties of the sources. The type of source is denoted by PSF for stellar, REX for round exponential galaxy, DEV for devocolors, EXP for exponential, COMP for composite, and DUP for Gaia source fit by different models. The flag_qual column selects sources with reliable redshifts, reasonable uncertainty, minimal contamination from nearby sources, low star likelihood, and free from imaging artifacts based on mask bits. The Z_best combines SDSS spectroscopic redshifts with reliable photometric redshifts. The table lists various properties, including magnitudes in WISE band 4, magnitude errors, and the origin of WISE measurements. It also includes mass estimates, rest frame magnitudes from said fits, and half-light radius of the legacy optical exponential, devocolors, composite model. Additionally, it provides errors on these properties. Table A.2 describes the columns for the component catalog, which includes the object identifier, radio right ascension and declination, errors on these, total flux density, peak flux density, and errors on these. It also lists the PYBDSF source code, LoTSS mosaic of the source image, and fitted Gaussian properties, including major and minor axes, position angle, and errors on these. Deconvolved properties, origin of the radio component, and parent source are also included. The appendix acknowledges the contributions of an anonymous referee, as well as funding and support from various organizations, including the UKSTFC, European Union's Horizon 2020 Research and Innovation Programme, and the Marie Skłodowska-Curie Grant Agreement. This research project was supported by a diverse range of funding sources and institutions. The UK's Science and Technology Facilities Council, STFC, provided grants, as did the Netherlands Organisation for Scientific Research, NWO, and the Leverhulme Trust. The Polish National Science Centre, the Ministry of Education and Science of the Republic of Poland, and the European Research Council's Consolidator Grant, ERC-COG, also contributed to the project. Further support came from the Comunidad de Madrid, the Italian National Institute for Astrophysics, INAF, and the NRW Cluster for Data-Intensive Radio Astronomy project. The University of Hertfordshire and the LOFAR UK computing facility also played a crucial role. The research relied on various open-source software packages, which are acknowledged for their contribution to the project's success. Astronomical projects, including the Baryon Oscillation Spectroscopic Survey, the Hobby-Eberle Dark Energy Experiment, and the Dark Energy Spectroscopic Instrument, have received crucial funding and support from various institutions and agencies. The Baryon Oscillation Spectroscopic Survey is funded by the National Astronomical Observatories of China, the Chinese Academy of Sciences, and the Ministry of Finance, as well as the External Cooperation Program of the Chinese Academy of Sciences and the Chinese National Natural Science Foundation. The Dark Energy Spectroscopic Instrument, which includes the Legacy Survey, receives funding from the U.S. Department of Energy, the National Science Foundation, and the Gordon and Betty Moore Foundation, among others. The project acknowledges the use of data products from the Near-Earth Object Widefield Infrared Survey Explorer, funded by NASA. The Hobby-Eberle Dark Energy Experiment is led by the University of Texas at Austin and receives funding from the National Science Foundation, the state of Texas, and private individuals and foundations. The project utilizes the Hobby-Eberle telescope and the Visible Integral Field Replicable Unit spectrograph for observations. The Dark Energy Spectroscopic Instrument collaboration acknowledges the use of Iokumduig, a mountain with particular significance to the Tohono O'odham Nation, and expresses gratitude for the permission to conduct scientific research at this site. This comprehensive list highlights the collaborative nature of these endeavors and the importance of acknowledging the support received from funding agencies, institutions, and individuals.